Today we will discuss about single phase half wave uncontrolled rectifier with L and RL load. So these are the very fundamental circuit. Once you are clear in this, automatically other higher order circuit we can understand. So today we will see with a inductive load. We have a AC supply connected through a diode to an inductive load. And if you see this inductive load, if you see as soon as the diode is forward biased in positive half cycle, as soon as the diode is forward biased, it is like a short circuited. And the Vs will apply across this VL or across this inductor L. So this Vs is equal to VL. So as soon as Vs is VL in the positive half cycle, and you can see, write down the equation. VL is L di by dt is nothing but Vm sin omega t. So if you find out what is the current you will find that Vm by omega L is 1 minus omega t cos omega t. So if you see here, the current starts at 0 as soon as the diode is forward biased, but the current continue to conduct till 2 pi radian, and that is what V naught also same as Vs, and current will continue to conduct. So how we will know that in the negative half cycle the diode must be forward biased? But if you see in the negative half cycle, you must see that the anode potential always will be higher than the cathode potential. And because this is, if you see here, this anode potential always will be higher than the cathode potential. That is why the diode will on the conduction state. And that is why when we have an inductive load, the diode start conducting from 0 to, and it continue up to 2 pi. We have seen in the resistive load, it is 0 to pi. Then the same concept we will extend for the uncontrolled rectifier with RL load. So this is my supply voltage, and through a diode it is connected to a R and L load, L and R load. So if you see that across the inductor there is a voltage VL, and across the resistor the voltage is VR. So you can write down a simple KVL equation. Vs is or V naught is equal to VL plus VR. So Vs is nothing but, we have seen that Vm sin omega t is the IR into L di by dt. So VL, if you find out, is Vm sin omega t minus VR. Now this is we will see in two ways of analyzing. First we will see analytical method of understanding the concept, and then we will have mathematical formulation by which you can derive mathematical equation, and after that easily you can do. For example, here it is my Vs, and if you see the I, the current or IR current will be, you know that we know that the current in case of a resistive load it will conduct up to 0 to pi, and in case of inductive load it will continue from 0 to 2 pi, and in the intermediate, if it is RL load, it will be between pi to 2 pi. So maybe if it is more inductive, the current conduction will carry up to or near towards the 2 pi, and if it is more resistive, then it will come towards pi. So if you see that the current will be somewhere, it will stop at an angle beta, and this IR current and IR current also you will see VR. So VR is I into R. So this is, you can see here, this is our current. So you know that VL is Vm sin omega t minus VR. At this point you can see here, this is our the VL is, this is positive, and at this point this will become 0, and after this point this will become the negatives. That means you can see that the area plus or area minus must be equal. That means you know that for an inductor, average voltage over a cycle must be 0. So this is what you can see, that the average voltage of this, because the area plus and area minus must be equal. When you add together, the average must be 0. And this way you can see that when it is turned on, the diode is on, and this is your Vs, this is your short circuit, and when it is off, it is off. So this is, you can see that it will start from 0 and conduct up to beta. Beta is called the extinction angle. Okay, now this beta, now we will see by using mathematical also formulation. You can see, if you see here, there are 4 distinct regions. So you can see that 0 to omega t1, and from omega t1 to pi, pi to beta, and beta to 2 pi. Okay, so this already we have discussed. Now we will try to derive the equations for this. So now if you want to find out your voltage, output voltage, you can show it will start from 0 up to beta. Now VDC is nothing but 1 by 2 pi integration 0 to beta, and Vm sin omega t d omega t. You will get Vm by 2 pi into 1 minus cos beta is your output voltage, and average output current is nothing but IDC is Vm by 2 pi r into 1 minus cos beta. Now if we see here the equation, we can derive the equation for this. Now we will see this same study with respect to different equations. So Vm sin omega t is IR plus LdI by dt. If you solve this one, there are 2 equations will come. One is a steady state solution, another one is a transient solution, and this is a e to the power minus t by tau. So where z is root over r square plus omega l square, and tan theta is omega l by r, and tau is l by r, which is time constant, and a is a constant. So complete solution is nothing but the total current I is equal to I steady state and I transient. Now the complete solution is here, and this you can write down the current as Vm by z sin omega t minus theta. Theta is your power factor angle plus a e to the t by tau. And to find out the constant at t is equal to 0. So your current was 0, just put these equations, you will get to the value of A, and put this value of A, it will come, this is I omega, this is our value of the current, and the final equation for the current is this one. When you simplify the whole current equation, then it will come like this. Now this is our final equation, and the current extinction angle beta. So you want to find out what is the beta when our diode will stop conduction. That point is called the extinction angle beta. But where the current will become 0. So when I will put a current is 0 at beta, so you can find out this is the equation. Okay. So this equation is a transcendental equation. It cannot be solved. You can solve by analytically, and numerically it can be solved. So we will take one simple example, a half-wave uncontrolled rectifier. For example, this one, the beta you must find out by this equation by iterative method. So this iterative method we want to see with an example. You see, for a half-wave uncontrolled rectifier circuit supplying a series resistive inductive load as shown below. The supply voltage is root 2 into 220 volt sin omega t. Supply frequency is 50 Hz, and parameters of R and L is given here. at 5 ohm and 16 milli. First one, sketch the load voltage and current. So you know that this is our load voltage, and already we have seen that the current will conduct up to from 0 to beta. Okay, and this is our current waveform. Calculate the extinction angle beta. So beta can be found out. This is our equation, and we understand that tan theta is 1, which is 45 degree, and you know that the initial guess for beta is 180 plus theta plus delta. So it is coming around 225 degree. So now the extinction, once you know the extinction angle, how you know? You put different values of the beta and find out what is this value. You can see that. So 225, the sine beta minus theta is equal to 0, 0. That means it is approximately 225. So even if 2-3 degree is a difference is there is no problem. And this is our extinction angle. Now by putting this extinction angle, you can find out by iteration, you can find out the beta is 225.8 degree. Now C is asked the average load voltage. We know that this is the formula for the average output load voltage is Vm by 2 pi into 1 minus cos beta. If you put it is coming around 84 volt. And next question asks calculate the angle of the maximum current. So di by dt must be equal to 0. So this will bring you the maximum current, okay, angle at which maximum current occurs. So we stop here. Thank you very much.